And I'll go through the chat and I'll delete this part of the chat if you want me to.
Okay.
How's the focus?
It's good.
Let's get started. Did you see the review sheet that I posted for us? I sent an announcement. Of course, I send announcements fairly regularly, but there is a review sheet with problems for test three.
Yep, I see it. I
Okay,
got it pulled up now.
what would you like to look at first?
I would say definitely working with, let's see,
Do you want to
say
work on
number two.
number two on the review sheet?
Mm-hmm.
Okay, I'm going to share my screen and I'm going to go to um, Blackboard and grab that. Usually I have this up already, but I was goofing around. The old Dr. Good was goofing. Oh, good. It's not making me do duo. Come on. Come on, Blackboard. Let's see if I can reload it. Doesn't want to load up. Where's my little reload thing? Not even letting me. Let me just hit this again. Oh, don't tell me Blackboard's down. Okay, can you read
Mm-hmm.
while this is working? I'm just going to lower this and I'll stop sharing.
Yep.
Can you read the problem to me?
Mm-hmm. I can actually probably do you one back or probably put it in the chat.
Really?
Yeah, I think so. Let me see. Yep. Just sent it.
Okay, so this is number two.
Mm-hmm.
So A is the set containing one, two, three, four, five, and six.
Okay.
What is B?
And B is containing the set of 2, 4, 6, and 8.
Is there a set C?
Yep. And then C is going to contain 1, 2, 5, and 8.
All right. Are there parts like A, B, C, D?
Yep.
All right. What's part A? What are we supposed to
Part
find?
so part A is gonna be A in unison with B.
A union B?
Mm-hmm. And
Okay, so
then
so let's just do this one first.
okay.
It's the set of elements that are in A or in B
Mm-hmm.
or both, of course.
Mm-hmm.
That's our
And
or
on a number
operator.
line, that includes the point fives, right? This is
Yeah,
what you
and
were
this
saying.
isn't number line. These are just what we call discrete sets.
Okay.
All right, so this is different from the real line interval notation. When we
Okay.
have finite sets, A only has six elements. But if it was a real line between one and six, it would have an infinite number of elements because it would have all the real numbers in between one and two and three and four. See what I mean? So this
Mm-hmm.
is different from interval notation. This is a lot easier, I think.
Yeah.
All right, so you tell me. So here's our solution. Can you see the red okay, or would you rather let me try the red? A union B. Is that visible?
Mm-hmm. I can see the red.
Okay, so we'll open our set brackets because it's a set. You tell me what is in A or in B or both because C union looks like or, right? It's our
Mm-hmm.
or operator. It looks like, the V.
Okay. So then it would be 2, 4, and 6.
Oh, that's A intersect
Oh, it's A
B.
intersect. So then I would
Yeah,
just list
yeah,
both down.
that's the and operator. See, because intersect, is
Mm-hmm.
that going to be the next one? Is part
Yeah,
B?
intersect is the other sign flipped, pretty
Is
much.
that part B?
Yes.
Okay, so that's our and operator. See how it looks like and because it's, upside down like that with the opening at the bottom. The or operator is cupped up like
Mm-hmm.
the union operator is different from the intersect operator. One is the or, union is the or. I'll just say intersect. And intersect is our and. So for
Okay.
the union, we're going to list everything that's in A or in B.
Okay. So then 1, 2, 3, 4, 5, 6, and 8.
That's correct.
Okay.
And A intersect B, if we were going to say it with words, can you tell me a sentence that describes this set?
Mm-hmm. Um, A intersects B at 2, 4, and 6.
Okay,
Or
but just
oh,
in general, can you tell me a sentence that we can write that describes in general what the set is? And then we'll give the answer. And you gave the right
gotcha.
answer. You gave the
Gotcha.
right answer. It's 2, 4, and 6. Those are the elements that are in A intersect B. But with words, can you write the
Mhm.
words?
Yeah, we set elements that are in A and B.
Okay, good. The set of elements that are in A and in B.
Mm-hmm.
Okay, and you've got the right set. Fantastic. What's C?
And then C is going to be A minus B.
Great. Can we write with words in general what set this is?
Set elements that are in A but not in B.
Perfect.
Okay.
I'm so glad that you're learning these definitions that are in A but not in B.
Mm-hmm.
And this is this is sort of like our uh, P and not Q. It's like the negation of an if then. It's sort of the negation of subset. It's exactly the elements in A that aren't part of B. All right, so A minus B.
Mm-hmm.
All right, so these elements have to start by being in A, but then we subtract away any of these from A that are also in B. So what's left?
So it's going to be 1, 3, and 5.
Very good. All right, how about D?
And then D is going to be A union B union C.
Just no parentheses. We don't need any. I'm just wondering if I put any.
Nope, no
Is it?
parentheses.
It's just A union B union C. So
Mm-hmm.
this is the set of elements that are in, are you sure it's union and not intersection?
Yep, it's both unions. However, E is going to be A intersects B intersects C, however.
Okay. So A union B union C is a set of elements that are in A
B,
or
A,
B
E, or
or
C.
C. All right. So what elements are in A or B or C?
It's going to be 2.
Oh, don't forget one because one is in A.
Oh, or gotcha. It's not and. So
Yeah, how are we
1.
going to help you remember that
Mm-hmm.
it's not and? You see how the upside down almost looks like an A if you put like a little bar across it?
Mm-hmm.
That can help you remember this is the and.
Okay.
Does that help?
Yeah. That's how I kind of usually try to remember it. I say that's probably the easiest way too.
And you can also think of the union like the when two people get married, that union is bigger than either one of them by themselves because
Mm-hmm.
two together makes more than one.
Okay.
It's one way to think of it.
All right, just writing that down. So we have 1. It's going to be so when it says it's in A or B or C, then it's just saying it it'll be all the numbers technically,
That
no?
that's right.
Okay. Okay. So then 1, 2, 3, 4, 5, 6, and 8.
Do you notice something about A union B union C?
Besides it listing all the numbers.
I'm just wondering if you see any difference between A union B union C and A union B. Do you see how those are actually the
Yeah,
same set?
they actually are. Hmm.
And you know why that is? The elements of C are already present in A union B. The 1 is already in A, so it's already in A union B. The 2 is in A. The, the 3 is in A. The 4 is in A. The 5 is in A. The 6 is in both A and B. And the 8 is already in B. So unioning A union B with C doesn't add any more elements because C is a subset of A union B.
Okay, that makes sense.
Are you ready for E?
Hmm. E is going to be A intersects B intersects C.
So if we were going to write this with words, how would we describe this set?
Set of elements that are in A and B and C and
Good.
in C.
And I would say and in B and in C if I had room, but this will do. We
Okay.
get the idea.
Hmm.
So these are the elements that have to be in all three of the sets at the same time. Are there any elements that are in all three of those sets?
So the elements are going to be that are in A and B and C. Two, four. Oh no, 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 just two.
That's right.
Just two.
Very good. How many more parts?
Right. And then have two more parts. So the next one is gonna be A, is it complements? The C, like the C up top is A complements.
A complement.
Okay. Going back to my notes.
That's it.
Yeah, it's just A complements.
So the complement is like our not operator.
Mm-hmm.
So it's the set of elements in the universe that are not in A. But were we given a universal set?
Sorry, say it one more time.
Did I give you a universal set? To play the
Mm.
complement game, we need a universe. So at
Yeah,
the,
the universal set is gonna be one, two, or 1 to 10, pretty much.
okay, so the universal set is the integers between 1 and 10 inclusive,
Mm-hmm.
including the endpoints. That's what I mean by inclusive. Yeah, to play a complement game, we need to know how big the whole universe is. So what elements are going to be in a complement? I'm going to bend this so that we can still see
Okay, and I wrote it down on my paper too.
our sets.
Um,
So what
so it's gonna be
elements?
eight
Okay,
and let's see, I think it's just eight. Just eight.
just eight.
Mm-hmm.
That 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 would be B minus A. A complement,
Mm-hmm.
just recall, we proved this in class. A complement is the same set as take the universe and subtract A. That was proved in class. That was one of our set equality proofs.
Mm-hmm.
So you start with the universe, but subtract away everything that's in A. If we drew a Venn diagram,
Gosh. So then it's just 7, 8, 9, and 10. Sorry.
that's right.
Yeah, 7,
So if
10.
this is our universe, and here's A, and here's B, and here's C, we can put the elements in there in the appropriate places. One is in both A and C. Do you see that? So
Mm-hmm.
one goes right there. Where does the two go?
2 goes
It's in all
and
three.
B and C.
And
Or no,
yeah,
all of them, all of them. So it goes
so it
right in
goes right
the
in the middle.
middle. And then
Where
3
does the three
goes
go?
in A, 4 goes in
So
A
three is
and
not
B.
part of B and three is not in C. So the three is out here in A by itself. See how it's
Mm-hmm.
outside of the circle of B and it's outside the circle that's C?
Mm-hmm.
I won't put a dot. I'll just put the numbers. All right. What else?
And then 4 is going
Four.
to be in A and B.
So four is right in there.
Mm-hmm.
What about five?
5 is in A and C.
Oh, I got to make this bigger then.
Mm-hmm. Right next to the 1.
I got to make this bigger because I have to fit a one in here and a five in here. Okay. What
And
about
then
six?
6 is going to be in A and B.
So we put six in here, but it's not part of C. See how it's outside of the C circle?
Mm-hmm. And then A is, or 8, oh no, sorry, 7 is going to be in the universe.
So it's out here, outside of any of the other ones,
Yeah. And then 8 will be in the universe. It'll be in B and it'll be in C.
but outside of A. So it's out
Mm-hmm.
here, outside of A, but in B and C. Good.
And then 9 and 10 will be in the universe.
Okay. So nine is out here and 10 is out here. All right. So A complement is everything that's outside of A. So it's everything that's anywhere outside of the circle that's A. And I think you already told me what those elements are.
Mm-hmm.
Seven, 8, 9, and
And
10.
10.
Yeah, because the seven is here. No, the seven is here. The eight is here. The nine is here. And 10 is out here. Okay, great. And what's G?
And then G, let's pull G back up. G is going to be or parentheses, A universe C,
Union.
union.
Because the universe is a set and it's got ears.
Yeah.
Union is an operator, not a set.
So then parentheses, A union C, and then outside of the parentheses will be a complement.
All right. So the first thing we're going to do is we're going to find A union C. And once we find it, then we'll find what's not in there. So what's an A union C?
So let's see. So A union C, put that to my notes. A union C
Unions
is
are
gonna be
or.
1, 2, 5, and 5. 1, 2, and 5.
No, that's intersection. So you see, you're using and. You're showing me the elements that are in A and in C, which is one, two, and five.
What is
But union is the or. This is or. Like, remember the or operator?
mm-hmm.
So this is like not P or Q.
So I'm listing all the numbers.
All the numbers that are in A or in C. And then we'll take the complement after we do that.
Okay.
So, right, we'll work inside parentheses first.
Mm-hmm.
So let's list all the elements that are in A or C. That's A union C.
1, 2, 3, 4, 5, 6, and 8.
Great. So finally, our last step gives us our final answer. Now we're going to take the complement of this. So all the elements in the union that are not in here.
Can you write it down in 1 second? All right, so he says to me all the numbers that
Are not in the set that we just built
so
because we're finding the
so
complement of the set we just built, which was A union C. So which numbers in the universe are not in here?
7, 9, and 10.
That's right. And if we wanted to understand it with a Venn diagram, here's A, here's C, B is there too, but here's A and here's C. The union of A and C is anything that's in A or in C, and the complement of that are the elements that are outside of A and outside of C. And those are the ones out here. And that was 7, 9, and 10. See? The ones that are outside of A and outside of C.
Mm-hmm.
There weren't any elements that were just in the set B and outside of A and C because B was a subset of A union C.
Okay.
Does that make sense?
Yeah, it makes sense.
Now, I'd like to just give a couple more problems because A union C complement, it's really
Mm-hmm.
a not. The complement is the not being applied to the or operator.
Mm-hmm.
So remember De Morgan's laws?
Yep.
So let's just, and this will be good review for the final two. Just recall De Morgan's laws. And we have two De Morgan's laws, and we have versions. We have De Morgan's laws for statements, and then we have De Morgan's laws for sets. And De Morgan's laws for statements tells us how we would distribute the not across the or operator. And it also tells us how to distribute the not across the and operator. Do you remember that? That's when we first came across De Morgan's laws.
Yeah.
Do you remember what the De Morgan's law is that
Mm.
tells us how to distribute the not across the or operator? What do we get?
I want to say it was not P and not Q.
That's exactly right. Very, very good. And what about the other De Morgan's law that tells us how to distribute the not across the and?
Not P or not Q.
Exactly. So it turns out we have corresponding De Morgan's laws in set land.
Mm-hmm.
This set that we just found was A union C complement. And union is like our or. I'm just going to use the set B, doesn't matter. If we take A union B complement, then we can see that that's going to be, well, A complement because the complement's getting distributed the way the not got
You know we're at
distributed.
the shower at 4.
So A gets flipped to A complement. What do you think happens to the union symbol?
The union symbol was going to be the and. So
The intersect, the
or the
and,
intersect. So the
uh-huh.
intersect
And then what do you think goes here?
is going to be B complements.
Perfect.
And then it's going to be equivalent to A intersects or A complements intersects B complements.
This is intersect.
Intersects.
It flips the intersect to the other operator. It flips the same way it flips or to and to or. It flips union to intersect. This is actually equality, not set equivalence, because I mean not statement equivalence, because it's not logical equivalence, it's set equality. So this intersect will flip to what's this symbol called? Do you remember?
Yep, it's gonna be the union. And the
Good.
union is the end. So
No,
our
union is
or
the
flips
or. Union is the or.
correct.
So, given that we have De Morgan's laws for sets, the same way we had De Morgan's laws for statements, we have set A. In fact, we had the universe. I'm just going to write the sets here so we can see them again. The universe, A, B, and C. So 1, 2, 3, 4, 5, 6, 7, 8,
And eight,
9,
nine, 10.
10. And was A 1, 2, 3, 4, 5, 6. And
Mhm.
B was the evens 2, 4, 6, 8.
And C is 1, 2, 5, and 8.
1, 2, 5, and 8. All right, so what we just found in part G was A union C quantity complement, right?
Hmm.
And we found out that that was the set that contained 7, 9, and 10. The work is on the other page. But according to De Morgan's laws, A union C complement should be A complement intersects C complement. Do you see that?
Hmm.
So let's actually find A complement intersect C complement and see if it turns out to be the same set. So
Uh,
first we'll find A complement
so
and then we'll intersect that with C complement. Okay, so what's an A complement?
a complement is going to be 1, 2, 3. No.
Do you know, can you say in words what A
Hmm.
complement is?
Because A it's going to be everything in set A that's in the universe.
No, no, let's go look again. Let's look at it one more time. A complement is the set of elements in the universe
In the universe that are
that
not
are
in A.
not in A. So let's just draw a picture.
So then it's going to be the 7 to 10.
You see, it's everything outside of A. Remember, we found A complement? It was the elements that are not in A. Okay. So, so what's not in A?
7, 8, 9, and 10.
Perfect. Now we want to find C complement. This is a 1.
And so it's going to be 3, 4, 6, 9, and 10.
And I think 7 too. Is 7 in C?
7 is not in C.
So it should be in C complement, right?
And
So
then
we'll
9.
throw that in there. And now we're going to find the intersection of these two sets. Remember, the intersection, it looks like sort of a soft capital A for and, all right? Also, if you have a hard time remembering intersection, if you have like two streets,
For
the
the intersect, it
intersection
meets.
is, yeah, part of both streets. It's this part of the street that's part of both streets, right? So
Yeah.
what is our A complement intersect C complement going to give us? It's a set.
It's
What's it?
going to be 7, 9, and 10.
And notice how these are the same because this is the first De Morgan's law at work. where the complement distributed across the union, and we get the intersection of the complements.
Mm-hmm.
All right, so now let's play the game with the other De Morgan's law. Let's find, in fact, let's use two different sets. Let's learn something new. Let's find B intersect C complement.
It's going to be,
So first we have to find B
mhm.
intersect C, right?
Yep, and B is going to intersect C at 2 and 8.
Very good. And now we'll find the complement of that. Everything in the universe that's not in here. So what's going to be a big set? What all we got
Yeah.
in there?
So it's going to be 1, 2, oh,
No,
sorry, 1, 3, 4, 5, 6, 7, 9, and 10.
perfect. That is B intersect C quantity complement. So which De Morgan's law are we going to try to work with? The first one or the second one here? Because we want to try to parallel what we did in G and H in these two parts.
We're going to work with the second one.
That's right, because we're going to distribute the complement across the intersection. So this set should be the same as what set?
That set should be the same as, oh, um,
Well, we're using B
A,
here. We're using B instead of A, and we're using C instead of B.
gotcha. Be the
So you
same
got to
as
just,
B
mhm.
union or sorry, B intersects,
All right. So if
right?
we
Because we're going
distribute
at
the
this.
complement across the intersection, it will flip the intersection to union.
And so B union C.
But it's no, but you have to also take the complement of the component sets. See how the De Morgan's law, when we distribute the not across the and, it does flip the and to an or, but it also flips P to not P and flips Q to not Q. So when we
Mm-hmm.
distribute the complement across the intersection, it changes the intersection to the union, but it flips A to A complement and it flips B to B complement. You see?
Mm-hmm.
So let's find a B complement union C complement. So let's first find B complement.
B complement, and that's going to be C. It's not in the universe. So
No,
1,
no, everything's in the universe. There is nothing that's not in the
but it's
universe.
just that are in B but are not in the universe is what I meant to say.
No, it's the other way around. It's things in the universe, but you don't want them to be in B. Yeah, it's the elements that aren't in
B.
B.
So in
It's
B but not
everything
in the universe.
outside of B. It's all these elements in the universe that are not in B. They are in the universe, but you don't want them to be in set B.
Okay. So 1, 3, 5, 7, 9, and 10.
Okay, so that's B complement. And now we're going to union that with C complement. So what is C complement?
I'll write it down. So C complement is going to be everything that's in the universe, but not in C, which means
Exactly.
it's going to be 3, 4, 6, 7, 9, and 10.
Fantastic. And now we're going to take the union of these two sets.
Mm-hmm. The union of these two sets are going to be, let's see, 3, 7, 9, and 10.
That's the intersection.
The union is both. So 1, 3, 5, 7, 4, 7, 6, 7, 9, and then finally 10.
Perfect. And you see how these two sets are the same set? Because these two sets will always be the same set because of De Morgan's law. Just like these two sets will always be the same because of De Morgan's law.
Mm-hmm.
I'm going to give you some do laters, okay?
Okay.
Okay, that'll give you some practice. And you can ask about those at a later office hour. Because De Morgan's law just keeps going. You can play De Morgan's law with three sets. So these are the two De Morgan's laws using three sets. If we had four sets, we could play De Morgan's laws with four sets, and so on and so forth. All right.
All right, I'm gonna take a picture of that real quick. And then I've got it. Did have another topic as well that I wanted to touch on. And it was going to be, let's see. I would say we can do three, number three.
So what
I
is
know it's
three
a little
sets?
bit similar. We go ahead and
Is it another set one? Let me see if it's loaded up yet in
okay.
my Blackboard. Oh, that's why I was complaining because I gotta use. Okay, let's see if it'll let me in. All right, I'm in. So we're looking at the review sheet. And we're looking number three. Yeah, interval notation. Okay, so test three review. Number three, the universe now is the real line. Okay,
Mm-hmm.
and we want to find -4, comma 1, union, soft bracket 0, 3, square bracket. B, we want to find -4, 1, intersect 0, 3, square bracket. C, we want to find -4, 1, complement. D, we want to find -4, 1, oh, that's a repeat. D, oh, D and E are repeats of B and C. I'll have to correct that later.
Okay.
All right, so sorry about that.
No worries.
Hmm, didn't realize that.
All right,
So
well, I
let's
have those
draw a
in
picture,
here.
Jessica.
Okay.
because these are real intervals. Here's the big caution. These sets, and I'm talking about square bracket -4, 1, and soft bracket to 3 square bracket, are not sets of integers. They are continuous intervals of the real line and have infinitely many elements. So, for example, you understand that when there's a soft bracket, we don't include the endpoint, but when there's a square bracket, we do include the endpoint. Do you understand that?
Yeah.
So, in particular, caution,
Hmm.
the set square bracket -4, comma 1 soft bracket is not just the set that has -4, -3, -2, -1, and 0 in it. It is not that.
Okay.
It's a lot more than that. And the set soft bracket 0, 3 square bracket is not the set that just has the integers 1, 2, and 3 in it. So what is -4, 1? Or maybe I should say, what are -4, 1, and soft bracket 0, 3 square bracket? If they're not this, what are they? Well, let's draw a picture.
Everything else outside of it.
Well, the complements would be everything outside of them.
Hmm.
But let's just start by figuring out if this is
Where?
0, okay?
Um,
And here's -1, -2, -3, -4, 1, 2, 3, 4, okay? So we'll
hmm.
we'll draw them both. And just try to line it up so that they're lined up.
Okay.
All right, so from -4 inclusive to 1 not including, it means we start at -4 and it's all the numbers between -4 and -3 and -3 and -2 and it's all these in between too. It is also the integers that are being included. But then we sneak up on 1, but we don't include the 1. It's like an open hole, okay?
Okay.
But we do include the -4. In the set soft 0, 3 square bracket, we're not including 0, but everything that's bigger than 0 up to and including the 3. So these are the two sets we're looking at, and they're both infinite sets, okay? They have
Hmm.
infinitely many elements. And it's critical to understand that when we're trying to find solutions to, like, what is the first set union the second set.
Okay.
It's, and remember, union is our OR operator. So it's any x in the real line. It's not just the integers, these are the reals. So, like, pi is here, Anything that's in this set or in this set or both. So,
-4, negative
and
3,
are we going to have a square? It's not just -4, -3.
square bracket then.
Square bracket,
Okay.
-4,
-4,
and we're going to,
-3, -2, -1, 0, and we stop at 1.
no, because it's
But
union.
but then 1, we go, so we just keep writing all in one line, so then it'll be 1, 2, 3, and then another square bracket to close it out.
These are not equal. It's not just the integers. It's
Hmm.
all these many, 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 infinitely many numbers that are in between the integers.
Gotcha.
That's why I gave you a homework problem where I asked things about pi and 2 pi and 5 pi, is I
Hmm.
wanted to emphasize that interval notation doesn't generally mean just integers. It's lots and lots of elements. It's all the real numbers that are in here or in here. They do overlap, okay? There's some
Hmm.
overlap. So when we get ready to try to figure out the intersection, what we're looking for is the overlap. The real numbers that are in both of these sets.
And the ones that are in both of these sets are going to start at, or it's going to be, so I know we're starting at 0. However, would the bracket be, I guess it would have to be a parentheses.
That's right, because the
Okay.
zero is not in the second set. Even though the zero is in the first set,
Hmm.
it's not in the second set, so it can't be in both. So it's not in the intersection. Very good.
Okay. So 0, comma, and then we're going to end at 3 with a square bracket.
It's an intersection. It has to be in both.
Oh, so we're ending at 1, 1 parentheses. So 0 to 1.
Very good. And then the complement of -4, where it's square bracket, -4, 1, soft bracket. Then we're trying to find everything that's outside of this set. So now we're looking at all the elements that are out back this way or this way. Do you notice how for the complement, I'm switching the delimiter? Like since -4 is part of this set, it will not be part of the complement on this side because it's part of, we call this set A, and call this set B. Do you see how -4, it can't be in A complement because it is in A? So the complement has to be everything that's less than -4 or elements that are over here on the other side past the 1. And since 1 is not an element of A, it's not in A, it will be in the complement. Does that make sense?
Yep, that makes sense.
So this piece, we'll call this, 1.
Hmm.
This piece is part of A complement, but this piece is also part of A complement. A complement is 1 union 2. We have to use a union because there's a break between them. Do you know how to write using interval notation all the elements that are strictly less than -4? Do you remember how to do that?
Mm, no.
All right, so do you understand that it keeps going to the left forever?
Yeah, it's infinity.
It'll be negative infinity in that direction, and it's
Hmm.
always a soft parentheses because negative infinity is not a number, it's an idea. It's just a concept of keep on going to the left forever. And then comma, and what'll be the number we put here to finish off this part of the complement of A?
The number that we're going to put there is going to be -4.
And will we use a soft bracket or a square
So,
bracket? Yeah, because -4 is in A, it cannot be in the complement. So
hmm
we'll exclude it. And then unions, because the elements in the complement are in one or two, right? One or two. Now we got to express the set that's over on this side of A. What should we start with?
we're gonna start with, let's see, square bracket,
Good.
and we're gonna have the number one, two, infinity, or comma infinity,
And what do I put here?
and we're gonna put a soft bracket.
Always. Okay.
hmm
So do you want to do later?
Yep.
And drawing a picture is key with these.
Yeah, the number line definitely helps it a lot. Makes
Yeah,
it
when it's intervals, you've got to draw a picture. With its finite sets, you don't really need a picture, right?
hmm
Let's let A be the set that goes from soft bracket -9.9. Oh, I don't want to make it so big because you're going to try to draw a picture. All right, -2, comma, 3 pi. That'll be hard. I'm going to do different. I'll just say -2 to 3, and I'll do soft brackets. I'll do several. B is going to be the set square bracket -1, 5 square bracket. C is going to be square bracket -2 pi, comma, 3 pi, soft bracket. And D is going to be soft bracket -4 pi, and then 2 pi square bracket. Okay. So find each. The universe is the reals always. Use interval notation to write your solutions, your solution sets. Use a union symbol as needed, because sometimes, like when we were dealing with the complement, the answer's broken up with a break in between, so we have to use the union, right?
Okay. And I've got a picture of that.
Well, let me give you some problems. So let's find a union B, a intersect B, a minus B, B minus A complement. And this is just lots of practice, okay?
Okay.
And then C union D, could, C intersect D, C minus D, D minus C, and D complement. And if you want more, you can make up more, you know, if K, J, K, L, M. I mean, you can just make up as many problems as you feel like doing, right? You can try to figure out A union B complement, and you can compare it with A complement intersect B complement. Like you can just go buck wild, right?
hmm
And see. intersect D complement. You can compare that to C complement union D complement. And you can compare, A complement, you can look at A complement minus B and B complement intersect A. You can do all kinds of stuff, right?
Hmm.
C complement minus D complement. I mean, you can just make up all kinds of stuff and just go crazy.
Okay.
So did you get your A, B, C, and D? And did you get these problems?
Yep. Took the last picture just now.
All right. Well, have fun.
Okay. And you don't have time for one more problem, do you? By
Yeah, I
chance?
do. I can give you,
Okay.
yep, because you're
Okay.
spending your Friday afternoon with me. I can give you a
Hmm.
little more time. What would you like to do next?
I guess a really good point to probably touch on is probably, I guess, a proof to kind of go over. Um,
We've got
nine and
lots of proofs.
yeah, 9 and 10 seem pretty similar, but I guess can we do 9 and 10?
We
Nine.
can't do both.
Okay, so which one
But
do you think is harder?
isn't nine the symmetric difference? We, so if you look at the class notes
Mm-hmm.
from day 22, we proved one direction of this set equality in class.
Okay, so
We
let's go back to
proved
that.
subset inclusion from the right to the left. And I left a do now for you, I mean, a do later for you to prove the subset from the left to the right.
Mm-hmm.
So I don't want to do that particular problem
Okay.
because I really want you to try and work that problem and you haven't tried it yet.
Okay.
So
Just
go ahead and try that problem on your own because it was a due later. And we will work it before the test on Tuesday, but you have to try to do it yourself first.
okay.
Now, listen, it's not that I don't want to work more proofs for you. It's just that if I work them all, then it leaves you with nothing to do.
Nothing, yeah.
However, if you were going to try to prove so you're looking at the problem, right? So you're
Mm-hmm.
looking at A union B quantity minus A intersect B, and you're supposed to prove that that's equal to A minus B union B minus A, correct?
Mm-hmm.
This is called the symmetric difference of A and B. Oops, symmetric has two M's. It's the symmetric difference of A and B. We proved one of these. See, for to prove set equality, just recall we must prove subset inclusion in both directions. What do I mean? It means we have to prove that the set on the left is a subset of the set on the right. And then we have to turn around and prove that the set on the right is a subset of the set on the left.
Okay.
That's what it means. So in day 22 class notes, so you should try to do it on your own and then look at the class notes to see how well you did. We proved this direction, right? We took an X from this set and we showed that it was in the set on the left. And then the do later was to prove this direction. Subset inclusion left to right. So that means you would take an element of the set on the left, just call it X, try to chase that element into the set on the right. It's called an element chasing argument.
Okay.
Remember? So when you have an element in this set on the left, you're going to break down, once you assume X is in this set on the left, you're going to break down what it means for an element to live in this set. And do you remember that we break down a compound set in the opposite order that we would build it? So we would first break down the set difference. If X is in this set, it means X is in A union B and X is not in A intersect B. See? Then we use what it means that X is in A union B. It means it's in A or in B. So we get two cases. But in both cases, we'll know X is not in both. And that we'll be able to show that means either X is in A minus B or X is in B minus A. In the case when X is in A, we're going to get that X is in A minus B, so it will be in this union. In the case when X is in B, it's still not in both, so it'll be in B and not in A. So it'll be in this component, so it'll be in this whole union. So you really, really need to review all the class notes because if you study those, I have given you all of the tools that you need, but you really
Okay.
have to study those and then do what I suggested. Try to write some proofs that are in the notes, and
Mm-hmm.
then if you have to peek, then peek, and then keep writing them until you can write them without peeking, and then you check and it's all correct. Then you know you're starting to understand the process, the procedure.
Okay.
But we will write these proofs before the end of the weekend or certainly by Monday night. But I want you to give them a shot, Jessica.
Yeah.
All
Mm-hmm.
right.
Definitely.
But I have just walked you through the proof in this direction, and the proof in the other direction is already in the notes.
Mm-hmm.
So
And I had
you
that
can
written down in
try,
my notes.
well, you can try to do this proof in right to left without looking at the notes, and then, you know, try this direction without looking at notes, right? Then you check the notes and then, try again, peek if you need to, check, try again. I know, and so on and so forth. Lather, rinse, repeat. Trying to think of another proof that we could do together. A minus B. Ooh, about A intersect B complement. Why don't we just draw that and see what it looks like? It's going to be what's in A and outside of B. No, yeah. So it would be this. We could try that one.
Okay. Writing it down still. B minus A intersects B. Okay, I got it.
All right. So let's just think about our strategy. Is our, you know, example two. Our strategy. We're going to take an X from this set, okay? So step one, assume X is an element of this set. A intersect B complement union A complement intersect B. And then in our step two, what do we show? Where do we want to show X lives?
We're gonna want to show that X lives in A union B minus A intersects B.
That's right. That's exactly right. That will prove
Hmm.
this subset inclusion. So let's start our proof. Let A and B be subsets of some universe. Okay, so
Hmm.
this out here is the universe. And now we're going to assume that X is an element of the set on the left, because that's the set we're trying to prove is the subset. And you already figured out what we wish to show. We wish to show X is an element of the set on the right, A union B minus A intersect B. So that's our wish. So what are we going to break down first? Let's just look at our hypothesis. Since X is an element of A intersect B complement union A complement intersect B, what do we know? What should we break down first? We break down the compound sets in an element chasing argument. We break
Hmm.
down these sets in the opposite order that we would construct them or build them. So what operator are we going to attack first?
The
Do you know what
or.
the
Sorry.
or?
The and, the
No,
and. Can you want
no,
to turn it?
it's
No,
the
it is?
no, the or, you were right. The
Okay.
union. We're
Okay.
going to break this down. Now, I don't know when you said or if you meant this or this. But this union operator is the OR operator, and it's the big operator. It happens, after these complements and intersections happen, right?
Hmm.
So we break this union down first. So let's break that down. What do we know about X if it's in this union? We know X is an element of what?
We know that X is an element of A and B
A intersect B complement.
intersects B.
It's
Okay.
A. Go on and just write the symbols at this stage. We'll break down this to an and in a minute, okay?
Hmm.
So X is an element of A intersect B complement. Let's keep going.
Union.
No, we're going to break the union down. We're working on breaking the union down to a word. That's what I mean by break down.
Oh, so then just or.
Or
Or A complements
We need a complete statement. X
or
is an
X belongs to A complements um
intersect.
intersects B.
Good. So we have an or in a proof. Or always means that we're going to use cases. That's always what or means. So here we're going to have two cases. And I'm even going to label them so I can keep track. Here's case one, and here's case two. In both cases, we still have the same wish.
Yeah, actually. Yeah, I remember this part in class.
We wish to show X is an element of A union B minus A intersect B in both cases, i.e., what do we really wish to show? Let's break down what our wish is just a little bit. How do we break down this wish?
We are going to break it down. I'm going to break it down by are we separating it? Like is A are we separating I'm gonna say the union?
How do we break down a compound set?
If it's A and B, then we just have A and then we also have B.
There's a general concept you need to try to remember. When we are trying to unravel, unpack, understand what this means, it's a compound set. X is an element of a compound, complicated set. Remember, we break down the big operator first. The last operator that operates is the first operator we try to translate into English. So do you see how the set difference or set minus is the last operator that would operate if we were trying to build this set?
Yeah, it's the very last operator.
So we're going to break that down first. That's one of the things you need to remember. There are kind of two main things that you need to remember. You need to remember the strategy. If we're going to prove this is a subset of that, assume X is in this set, and then show X is in that set. The other thing to understand is once you understand the hypothesis, when we're breaking down the hypothesis or understanding the wish, we have to unravel these compound sets, and we do that in the opposite order that we would build them. So here, for example, this is hypothesis. We wanted to break this down. We attacked the union and we changed it into English or. Now we're trying to look at our wish a little closely. We're going to attack this last operator first. What does it mean that X is in a set difference applied to these two sets? What does it actually mean? It means X is an element of A union B, right?
Mm-hmm.
And what else does it mean? What does this set minus mean? You know this.
That
X is not an element of
X is not an element of A or because
intersect.
A intersects B. A intersects B. X is not
Okay.
an element, correct.
All right.
X does
So
belong to A universe B or A unison
union,
union B,
union.
but does not belong
Like
to
the
A.
student union is where all the students get together and everyone's in there. Well, A union B is where A is the set where A and B get together and all the elements of both A and B are in their union. Just like you all go to the student union, all the students can go there. See what I mean?
Mm-hmm.
That's what union means. All right. So we have two cases. In both cases, we're going to try to show X is in A union B and X is not when A intersect B. Do you agree?
I agree.
So let's do it. Case one. Let's attack case one. Case one is the case where X is an element of A intersect B complement. So let's suppose or assume or let, I'll just say suppose X is an element of A intersect B complement, right? And then we'll prove this wish. We'll prove X is in A union B and X is not in A intersect B, and that'll get X right where we want it in this set difference. Then we'll do case two. So now we're going to break down what it means for X to be in A intersect B complement. So by definition of this is by definition of union. This is by definition of set difference, but it's a wish, so I don't have to write that. So what is the operator we're going to break down first as we try to unravel what it means for X to be in this set? What's the last operator that
By definition
operates?
of difference.
I don't see a set difference here. X is in A intersect B complement. I see a
Intersection.
complement and I see an intersection.
Intersection.
If you were going to build this set, which operator would you use first?
The first one I'm going to use is
Well, you have to know what A is, and you have to know what B complement is before you can take their intersection. Does that make sense?
mm-hmm.
So you would first figure out the complement of B. So you would be using the complement operator first. After you figured out what B complement is,
Then
then
I'll
you could take the intersection of that with A. Do you see?
gotcha. Yep, so I'm working backwards. Okay.
So that's working forwards if you were constructing the set, but now we're deconstructing the set. We're trying to deconstruct what it means for X to be in A intersect B complement. So we're going to deconstruct by attacking sort of the big operator, the last operator that operates, and that would be the intersection. So by definition of intersection, or by definition of intersect, X, you tell me what it means for X to be in this intersection.
For the X to be the intersection, it means that it intersects at A and B complements.
So well, let's make two statements from that. It means X is an
Intersects
element
at
of
B complements,
A,
A,
or, and what's the other
and
statement?
X intersects at B complements.
X is an element of B complement. X is an element of. Its relationship isn't intersecting with sets. It's an element of a set or it's not an element of a set. That's the relationship of the element X with the sets. The sets relation to each other, they can intersect with each other. We can take the complement of a single set. We can take the union of sets. But the relationship between X and sets is the element of or not an element of. Okay?
Mm-hmm.
So look, this is atomic. We can't break down the fact that X is in A any further. There's no set operators involved. Yeah, there's the element of, but this is it. A is a simple set. It's atomic. We can't break it down. It's not a compound set. But we can still break down this statement a little more because B complement is using a set operator. What set operator is being used in the compound set B complement? It's
The
called the complement.
complement. The
Yes.
complement is
So
being
let's break down what it means. Since X is an element of B complement, what do we know? What does that tell us about X?
it tells us
That X is not
that
in
X is
B.
not in
And
B.
yeah, by definition of complement. And that's complement with two E's. So now we've got these two atomic statements that cannot be broken down any further. It tells us X is in A and X is not in B. So this is as far as we can go now, as far as breaking stuff down. Once we've gotten to the end of the line, breaking down the hypothesis, now we turn to our wish and we try to build back up to get X in the set we wish. See what I mean?
Hmm.
X started in this set. We break it down until we can't break it down any further. Then we're going to build up from these atomic pieces to get back to now our wish. We are really trying to find that X is in A union B and that X is not in A intersect B. Well, since X is in A, let's just let our wish guide us. Where do we want X to wind up? Where do we want X to be an element of? Look at our wish.
We want it to be Sarah, say that one more time.
Where do we want X? What do we want X to be an element of? Where do we want
Element
X to
of
land?
A union B.
We want it to be an A union B. And we know that that means we want to show X is in A or X is in B, right?
Hmm.
Well, it's an A. In this case, we broke it down and we know X is an A. So since X is an A, we know X is an element of A union B by definition of union.
Okay,
Because it's
that's
in
good.
A, it's in A or B, right? So
Hmm.
the definition of union says, hey, if you get X in A or in B, you can say X is in A union B. So we just used X in A to get X in A union B. Now, what else do we need to show about X to get our wish?
That X does not belong to A intersects B.
Great. What are we going to use that we have to show X is not an element of A intersect B?
Well, we know that X does not intersect or does not belong to B.
Right.
So if it does not belong to B, it can't belong to A intersects B.
That's right. Because if it doesn't belong to B, it doesn't belong to both. So since X is not an element of B, we know X is not an element of A and B, A intersect B by definition of intersect. It
Hmm.
can't be in both if it's not in B. So look, we just got. See, this was our wish. We wished to show that X was in A union B, and we wished to show this because our ultimate wish was to show that X is in this set difference. Well, we're there. We've got that X is in A union B, and we've got X is not in A intersect B. So we'll be able to say X is definitely in A union B minus A intersect B by definition of what?
Definition of intersection.
Since X is an element of A union B and X is not an element of A intersect B, we can say X is an element of A union B minus A intersect B by
Or,
definition of
or is
what?
it both? Is it not? It's not both.
We already proved since it's not in B, it's not in both. We already showed that it's not in A intersect B. Okay, we got there. We got here and we got here.
Yeah.
So now we're using those facts. Because why did we
Oh, is
even
it
know?
difference? Difference.
Yeah, because
Difference.
that's what it means.
Because
Because
the
this is
subtraction
see how
symbol.
we
Right.
add we put these two statements together
Hmm.
with this. So that's what I mean by definition of set difference, because we got it in the first set and not in the second.
Okay.
Now you do case two later, all right? It's going to look a lot like case one. See, case two, you're going to have X is in A complement intersect B. In case one, we had X is in A intersect B complement. It'll be a little different. You're going to get a little bit different facts, but you'll still be able to get this to get the wish. This is the ultimate wish to get X in this set difference, right? Because we're
Hmm.
trying to prove Subset inclusion in that direction. We started with X in here, see? And we're trying to get X over there. Remember?
Yeah.
So I'll put this up here, proving A intersect B complement union A complement intersect B is a subset of A union B minus A intersect B. Okay. We started with an X in here, and now we're pushing it to get our wish, just to get it over there. So you do case two and get X in, our ultimate wish, which was to get X in A union B minus A intersect B. You can do that in case two using this hypothesis of case two. Do you want me to take a scan of these notes?
I'm actually writing everything down on the last
Good.
line.
That's great.
Just having
That's
a look.
better. That's even better. All right. And then, of course, if you
Hmm.
want even more, another do later is now to prove the other direction, that A union B minus A intersect B is a subset of A intersect B complement union A complement intersect B. So you can prove subset in the other direction. Okay. Well, I need to take my dog for a walk. He's been a good boy.
Okay. All right. Thank you. I gotta probably go feed my bunny. She's
Oh, what
waiting
kind of
for
bunny
me.
do you have?
I had a mini Rex.
A mini
I have
Rex.
allergies, yeah, so she's hypoallergenic.
Cool. Do you get little bales of hay for it?
Yep, yeah, my mom bought her I think like 4 big bags at the beginning of the semester. So even though she's not a fan of animals, she won't admit it to this day that she likes sage, but it's growing on her.
We had a bunny rabbit, but we made one mistake. We didn't learn to clip its nails. And so when we went to a 4-H exhibition, the lady that knew a lot about rabbits fussed at us and said we needed to clip our bunny rabbit's nails.
Mm. Yeah, I don't do it because she fights me on it, so I take her to the vet just weekly. But yeah, I'm not putting up with it.
I'll see you later. Have fun with your bunny and have fun in New York. Be careful in New York, okay?
All right, will do. Thank you again.
You're welcome.
Bye.
Bye.